So in today's lecture we are going to discuss the Bragg's law in reciprocal lattice, or this can be also called as Ewald construction in the reciprocal lattice, or also this can also come in exam as your Bragg's law in vector form. So since in the X-ray diffraction we have in that established that to get the X-ray diffracted from any lattice point in direct lattice, Bragg's condition should be satisfied. That is 2d sine theta is equal to n lambda. Only for that this condition, when the your lambda and d matches, your X-ray diffraction will takes place in the direct lattice. So similarly, in the reciprocal lattice, your two X-ray diffraction happen. We need Bragg's condition. The Bragg's condition should also be satisfied in the reciprocal lattice. So here we are considering a reciprocal lattice in the reciprocal space. So in this case, suppose X-ray is incident like this in this direction. So this line representing the incident plane, because each line in this reciprocal lattice is representing a plane. So let us consider this is vector AO having length 1 by lambda. So then, by considering this vector and taking A as a center, we will draw a circle in this reciprocal lattice. Since this is 2D reciprocal lattice, so this will be circular. So since if you take three-dimensional reciprocal lattice, then this will be sphere. Okay. So by taking A as a center, we will draw a circle. So now let us consider that this circle that intersect a reciprocal lattice point at particular point B having Miller indices S dash, K dash and L dash, which can also be written N, H, N, K, N, L, where N is the largest common integer between this prime Miller indices and non-prime Miller indices. This is the common factor. So now by taking O as the origin, we will draw a vector. This is a reciprocal lattice vector OP, and this is perpendicular or normal to your direct lattice plane. Okay, so this is OB, this is a reciprocal lattice vector. So what it will have a length, what will be its length? This will be 1 upon DHKL, so D H dash K dash L dash, or N upon DHKL. DHKL is spacing between the two lattice planes of direct lattice. So this will be the length of this we have discussed in the your Miller indices, that is interplanar spacing. So now I will take a lattice plane perpendicular to this vector. This is perpendicular or normal to this or reciprocal lattice vector. So you can say that this is in direct lattice. So and it is making an angle theta with your incident plane. This is your reflective plane. So let us draw this line vector AB. So this represents incident plane and this represents diffracted plane. So now diffraction will be, the X-ray will be diffracted by this point B. So now from here in this reciprocal lattice we will deduce your Bragg's condition, for which your this X-ray diffraction it is taking place. So now by using your this right angle triangle OAE, so now by using right angle triangle OAE, this is your perpendicular, this is your base, this is your hypotenuse. So we can calculate your this OE. So OE is perpendicular, so we will have to find out the sine theta. Sine theta is perpendicular, that is your OE, this is vector, we will take magnitude OE upon, this is hypotenuse AO magnitude. So OE, I'm taking a simple magnitude, this will be AO sine theta, AO sine theta. So now this Since we know that AO is equal to 1 upon lambda, so therefore, which is the radius of your circle, OE will be 1 upon lambda sine theta. So here your OE is 1 upon lambda sine theta. So now, since from this figure you can say that OV is twice of OE. OV is equal to twice of OE. So since from figure your OV vector magnitude is twice of your OE magnitude, so therefore your OV is equal to 2 on lambda sine theta. OV is equal to 2 upon lambda sine theta. Also, I have told you that this is your OV is your reciprocal lattice vector, and it is its magnitude will be n upon d h dash h d h k l. So since OV is also n upon d h k l, this is by definition, this is the magnitude of reciprocal lattice vector, that is 1 n upon d HKL. d HKL is your interplanar spacing between HKL plane. So this, therefore, equating these equations, so you will get your 2 upon lambda sine theta is equal to n d HKL. So therefore, by rearranging, this will be 2 d HKL sine theta, this will be n lambda, and this is nothing but your Bragg's law. So only for this condition in the reciprocal space your X-ray diffraction will takes place. Only for this condition, when your DHKL and your lambda will match, where and this order of reflection, it is now it is there is a one point which is worth remembering in your the reciprocal space, where n was your largest common integer between your integers, that is HKL dash KL dash L dash, which is related to your simple indices by n, that is NH N K N L, where n was your largest common integer between common integer to H dash K dash and L dash to this HKL. Here it is reflecting here, you are transformed into your order of reflection, where n is order of reflection, which is related to your largest common integer. This is very important condition. This is your Bragg condition, which is only satisfied for the values of d, HKL and lambda. So now let us consider one condition, that if this circle does not intersect any lattice point of your reciprocal lattice, so then there will be condition that this X-ray will not diffracted. That means there will be no diffraction, X-ray diffraction, when this circle will not intersect any of these points of a reciprocal lattice. So which means if this not diffract, which means your what is OA, AO is equal to 1 upon lambda. So in this case your uh, AO will be less than 2a. 2a means a means DHKL, which means it can also be called as lattice parameter. So this is AO, which will be less than 1 upon 2a, which means that your this circle will not intersect any of this point on lattice point of the reciprocal lattice. So for that case, this will be the condition, that means AO is equal to 1 upon lambda. 1 upon lambda will be less than 1 on 2a. So you can say that lambda will be greater than 2a. So this will be the condition when your circle will not intersect any of the points of reciprocal lattice. So in this case diffraction will not happen, and if your lambda is less than equal to 2a, so that means there is greater possibility of the circle intersecting the point of your reciprocal lattice. So for this case your X-ray diffraction is likely to be happened. तो अगर मैं सिंपल वर्ड्स में बोलूँ तो इस कंडीशन के लिए जो हमारा सर्कल इवॉल्व सर्कल है या दैट विल नॉट इंटरसेक्ट एनी ऑफ द रेसिप्रोकल लैटिस पॉइंट्स, so that means there will be no X-ray diffraction, and for this case your circle will touch any of touch or intersect any of the reciprocal lattice points. For this case X-ray diffraction is likely to be happen, so there will be X-ray diffraction for this case. So now further we are going to deduce the vector law, Bragg's law in vector form. So this is your evolved sphere and this was your incident plane, and this vector around which this evolved circle is constructed, and this was your OV is your reciprocal lattice vector. So now I have written this this was AO was 1 upon lambda. So since we have studying your reciprocal lattice, I have told that in reciprocal lattice we will multiply a constant of, that is 2 pi to the magnitude of a reciprocal lattice. So since this is 1 upon lambda, if you multiply it by 2 pi, the 2 pi upon lambda is nothing but is your wave vector. So this is your wave vector k, and this is your reciprocal lattice vector, this is g. So since I have told you this before that if in reciprocal lattice or reciprocal space, if you want to move from one point to another in the reciprocal space, so you have to apply the translations in the reciprocal lattice. So these translations are described mathematically by using a vector that is known as a translation vector, which is it is denoted by g, which is equal to h a star vector plus k b star vector and plus l c star vector, where h k l are the Miller indices of particular plane, and a star b star and c star vector are your fundamental primitive translation vectors of reciprocal lattice. So these I have written. So since these are the vectors, this is k vector, this is g vector. So now by using the triangle law of vector addition, to this structure, so we will get by using triangle law of vector addition. So AB vector, this is a resultant, this will be AO plus OB. So this is represented by K dash vector, AO is equal to K vector plus this is translation vector of reciprocal lattice. So this is the equation number 1. This is this I have read by using the triangle law of vector addition to this vector diagram of evolved sphere, evolved circle. Evolved sphere is basically in 3-dimensional. So since this is circle, so these will be the radius, these will be the radii of this circle. So since we know that the radii in any direction will be the same, so since your AO vector and AB vector will be equal because they are radii of same circle. So since you can write that what is AO vector is equal to K, what is AB which is equal to K dash. This is equation number 2. Put the value of K dash into equation number 2. Value of K dash is equal to K plus G. So by using equation 1 and 2 we have, that is put the value of K dash into this equation. K will be K dash is equal to K plus G. So now I want to find out the magnitude. So square, take the square, this will be so this will be the square and this will be simply this will be this will be this is whole square, this will be K vector square plus square plus 2 K vector dot G vector. So since this will be cancelled, so you have 2K dot G is equal to plus G square is equal to 0. This is equation number 4, and this equation number 4 represents the vector form of your Bragg's law. This is the vector form of Bragg's law. So since this can also be written as 2K dot G is equal to minus G square, or 2K dot G is equal to minus G vector square. So since G is a translation vector in your reciprocal lattice, so this G can also be negative. So G or minus G vector, they are a translation vector in your reciprocal lattice. So this can also be written as like this. Question number 5. So this is the vector form of Bragg's law in reciprocal lattice, and this is very important. One thing I want to tell you here, that you will be confused how K is there and G is there. So since from the previous figure, this is AO is 1 upon lambda, since AO is equal to 1 upon lambda, so since in reciprocal lattice we multiplied by a constant by 2 pi, so suppose this is multiplied by 2 pi, so this will be 2 pi upon lambda, and this is nothing but wave vector. So therefore K is how K is reduced in this diagram, and G OB is equal to G. So G is here nothing but G is 2 pi times your vector OB. That's how these twos are written in this vector diagram.